All right, hello. We are going to continue with section 6, or chapter 6, and look at section 2, which involves circular motion. So previously we talked about projectile motion, launching objects up into the air, and now we're going to talk about circular motion. Okay, so let's talk about what circular motion is. So if we think about acceleration, do objects moving in a circle at constant speed accelerate? Well, let's think about what acceleration is. Acceleration is the change in velocity over a change in time. And we know that velocity can be broken down into speed in a given direction. And so if we change speed or direction, that means we are changing velocity, which means we are accelerating. Well, if we're moving at a constant speed, we know speed's out, we're not going to be changing speed. But if we're moving in a circle, we are constantly changing our direction, and so this would mean that we are accelerating. So things moving in a circle at constant speed can be accelerating, and that's what we're going to talk about today. Okay, so acceleration is change in velocity, which ends up being our change in direction. Okay, so if you are doing donuts in the parking lot, not something I would recommend, but if you decide that's what you want to do, then you would be changing direction. Sorry, Shesta's going crazy with her bone. She picks now to do this. So if you are doing donuts in the parking lot, then you are changing direction, and you are accelerating. Okay, so let's talk about how to describe circular motion. We have what's called uniform circular motion. So if you think about what the word uniform means, everybody is the same. And so we're going in the same type of circle. So this is movement of an object at a constant speed around a circle with a fixed radius. So our circle is exactly the same all the way around, and so our radius, our center of our circle to the outside, is the same all the way. So we're going to label our radius as r, okay, and so we have our circle. It's not a very good circle. And then this would be our radius from the center to the outside. So r is the vector that describes the position of the object relative to the center of the circle. And since it's a vector, we're going to add an arrow on it. Okay, the length of the position vector will not change, and that's because the center of the circle isn't going to change. So whether I draw my vector going out to the right, or I draw my vector going straight down, if this was a perfect circle, that length would not change. However, what can change is the direction that it is pointing. As we're traveling around the circle, we're going to be at different positions on the circle at different times, and so the direction of our position vector will change. We can use this to find velocity. And so what we need to do is find what's called the displacement vector over the time interval, because if you think about the velocity equation, velocity is equal to the change in distance over the change in time. Since we're traveling in a circle, we're going to look at, instead of distance, we're going to look at displacement as far as radius, so center to the outside. And if we look at the distance that we have traveled that way over time, that gives us velocity. So if we have a circle, that one's a little bit better this time. Here's our radius. Here's our initial distance vector. And let's say that we travel O to here. Okay, well this then represents our displacement vector from start to finish over that time interval. That's the distance that we have traveled. We can use that to find velocity. So we know that our change in r, remember we're using r instead of distance in this case because we're talking about a radius, is equal to r1 minus r2. If this is what we're calling r1 and this is our r2, then this displacement is our change in r. Okay, and then we can also put a velocity vector onto this drawing. The velocity vector has the same direction as displacement, but a different length. Okay, and we're going to draw that in a second. Let's get a little bit more information. The velocity is also at right angles to the position vector. So this means that it is tangent to its circular path. So let's talk about what that means. If this is my position vector, my velocity vector is going to be tangent to it. Oops, that's not one. A tangent is a vector that on an arc occurs at this one point and then goes off in a straight line from that one point. And so if this represents our displacement vector, then this is our tangent at that point. We would call this v1. And then if this is our displacement vector, this goes off at a tangent and we would call this v2. So it's at right angles to the position vector and tangent to its circular path. If I took these two vectors and put them together, my resultant would be in the same direction as the change in r, so this being my v1, and this being my v2, and this being my change in v. And so the velocity vector is in the same direction as the displacement vector, but they are different lengths, and each of those velocity vectors is at a right angle to the displacement vector and tangent to its circular path. So the direction will change, but the length will stay the same. So now let's talk about how to put that in with acceleration. Okay, so we know that acceleration is equal to the change in velocity over the change in time. And we know that change in velocity there's two velocity vectors subtracted from one another. And so we know that acceleration is in the same direction as the change in velocity, but acceleration in this case points toward the center of the circle. So let's go back to our circle. Here's our radius. Here's my initial position vector. Here's my final position vector. Just is going crazy. I'm sorry. Here's my velocity vector that is tangent and perpendicular. Here's my other velocity vector that is tangent and perpendicular. Here's my displacement vector. Now I'll draw my velocity displacement vector over here. Okay, so this is my v1, this is my v2, here's my change of velocity. And so now, if I look at my acceleration, it's in the same direction as the change in velocity, but now it's going to point towards the center of the circle because acceleration is what's called center-seeking or centripetal. And the direction of acceleration changes, but the length will remain the same. So what we'll have then is at different points, we will have this acceleration pointing in towards the circle. Now, conceptually, you would need to understand this, but you don't need to be able to replicate this drawing. You just kind of need to understand theoretically where this is coming from. Okay, so the acceleration vector in uniform circular motion, okay, because we have this constant circle with these same distance for displacement vectors, they're just in different directions. Acceleration is always going to point towards the center. And so we call that more specifically centripetal acceleration because it is center-seeking. Okay, so let's kind of talk about a little bit of how to calculate this. So centripetal acceleration, we're going to use a small c to indicate centripetal. And this is equal to v squared over r. So I would put this on your note card. Okay, for chapter 6. So this is what we're going to use, and whenever you have something traveling in a circle, this is the acceleration. So to solve for v, or speed in this case, we need to measure its period. Now period is time, but more specifically, it's the time to do one revolution. Okay, and so like a record going around once, or a bicycle wheel going around once, that's the period. So t is the time needed to make one revolution, and it's a capital T instead of a small t. So the object will travel one circumference of the circle in capital T in the period, and so circumference is 2 pi r, which is equal to the distance. So we know that really, if we take velocity, we know that velocity is equal to change in distance over change in time. And now if we relate it to a circle, we know that the distance traveled is one revolution, which we know is equal to the circumference. And we know that the time it takes to do that is specifically known as the period, or capital T. And so now our rearrangement of velocity becomes 2 pi r over capital T. And this is specific for circular motion. So if we take that and we put it back up into our acceleration equation, we know that acceleration is equal to v squared over r, which is the radius. So let's take our rearranged velocity equation, 2 pi r over t. I know I need to square that, and that goes over my r. Okay, so now let's square some things. If I square 2, that becomes 4. Pi squared just becomes pi squared. R squared is r squared over t squared, and this is all over r. I'm going to make it r over 1. Now we have a fraction over a fraction, and so we want to multiply by the reciprocal. And because I have an r on the bottom, that's going to cancel one of those out, and cancel that one out completely, and so I end up with what I have right here, which is 4 pi squared r over t squared. And this is equal to centripetal acceleration. And again, this is something I would put on my note card. Okay, so because we have centripetal acceleration, we can also have centripetal force. And so there's an equation for that too. So for an object moving in a circle, this is what we would specifically call centripetal force, since we have centripetal acceleration for an object moving in a circle, and that's the acceleration. We know that net force is just equal to mass times acceleration, and so specifically for centripetal force, it's equal to mass times the centripetal acceleration. So for example, like the force acting on the Earth is the sun's gravitational force. Because of that circular, it's not circular, it's more elliptical, but kind of the same idea. This is also true for something like the force on a hammer for track. So here she's got this string in her hand, and then there's this object attached to the end, and you swing it around, and then you let it go, and it goes a far distance. That's also centripetal force. Okay, so anything spinning in a circle, you could take a bucket of water, and if you spin it over your head really fast, the water will stay in the top of the bucket. So you could try that if you want, if you're feeling brave. And that's the same idea, and the same reason that the water stays up there is due to centripetal force. If you've ever been on one of those amusement rides where it spins and then they take the floor out and you like press to the side, I will never go on one of those, but that's the same idea. So if you want to experience centripetal force, there you go. Okay, so we will be completing some practice problems in class, but if you feel like you have a good grasp on this, go ahead and try them beforehand. And then same idea, here's the homework. Okay, and otherwise we'll answer any questions you have in class. Have a good day.